So we are proving everything for a circle action first, okay? Because everything is simpler in a circle action. The equivariantly closed forms, the equivariant differential forms are just polynomials in U with coefficients in invariant forms. And the Cartan differential is fairly simple to write down and so on. Okay? But we can generalize it to torus actions very easily, okay? Because basically we're using the fact that the group is compact and it's abelian. Okay? So everything will work for a torus action also. It's not too different. And then we can generalize to an arbitrary compact Lie group action. Okay? But then some of the theorems will not be the same because then you don't have the abelian property. So some of the theorems will not work. Okay? But yeah, most theorems for a circle action will generalize to a torus action. Okay? And so we're going to start with Borel localization for a circle action. And let me state the theorems again. So suppose S1 acts on a compact manifold M with fixed point set F. Okay? And we know now that F is a submanifold. Mm-hmm. Then Borel localization says that there is a ring isomorphism from the equivariant cohomology of M to the equivariant cohomology of the fixed point set. Well, this ring isomorphism is given by restriction. So the restriction map is an isomorphism when you localize with respect to U. And the restriction map is a ring homomorphism, so therefore this is a ring isomorphism. And because the fixed point set usually is simpler, so this gives you some information about the ring structure of equivariant cohomology. However, you have to localize, so sometimes you don't actually get the complete ring structure of the equivariant cohomology of M. Okay? Yeah. So we'll do a couple of examples to see how to apply this theorem. But first, let's prove the theorem. Okay. Now, I proved last time that F is a manifold, a submanifold, and I also proved that it's a closed subset. Okay. So that's why I need the compactness of M. So since F is a closed subset of a compact manifold, it is compact. And last time we proved that it's a submanifold, so it's a compact submanifold. Now, a compact submanifold has an equivariant tubular neighborhood. Okay? The F is also G invariant. And that neighborhood I will call NF. So since F is G invariant, it has an equivariant tubular neighborhood, NF. Which is isomorphic to the normal bundle. Of F in M. Yeah, so now let me see. So NF by definition is G invariant. Okay, so it's a G invariant open set. Right? Now, can you think of another open set so that together you will have an open cover of M by G invariant open sets? I have a G invariant open set here, NF. Okay. What's another open set that would, together with NF, cover the manifold M?
It's M minus F.
M minus F, yeah. So M minus F it's also G invariant, because F is G invariant, is a G invariant open subset such that NF and M minus F together is an open cover of M by G invariant open sets. Okay? So you can write down its Mayer-Vittora sequence. By the equivariant Mayer-Vittora sequence. So we have a long exact sequence. HK of M, G. These are all G manifolds. HKG NF plus HKG M minus F. hk minus 1g of the intersection nf. And then here it goes to hk plus 1g of m. Okay, so we have this long exact sequence. Yeah. Okay. Now, let me see. So, what do you know about the action of, well, here G is S1. Uh-huh. Right. Yeah. Let's see. Sometimes I write G. Yeah, sometimes I write G, so I'll say where G is S1. I'm only looking at S1 actions right now. Okay, now, what can you say about the action of S1 on this open set, n minus f? Locally free, because you've taken away the fixed points, so the action now has no fixed points. And if S1 acts with no fixed points, then the action is locally free. Now, if the action is locally free, that means when you localize, it will give you 0. Okay? So, now because localization preserves exactness, if you start with an exact sequence and you localize, it's still exact. So I'm just going to take this sequence and I localize with respect to u. Okay? And it's still exact. Okay, so by the equivariant Mayer-Victoria sequence, we have a long exact sequence, and then we localize and it's still exact. So because localization preserves exactness. Okay? And you know that some of the terms are 0. So this is 0 because S1 acts on m minus f locally freely. Okay? Now what about this one? What is this term? It's also 0 because this is a subset of m minus f. So again, the action has no fixed points here. So this is also 0. Okay. And so this is 0. Because the action has no fixed points, so it's locally free. And so you see that this will have to be an isomorphism, okay, because it's bounded by 2 0 terms. Okay? Now, let's write this down. So in this long exact sequence, now, so S1 acts on m minus f with no fixed points. So the action is locally free, and the equivariant cohomology is U torsion So when you localize, you get 0. Okay. And similarly, for the same reason, the equivariant cohomology of the intersection localized at U is also 0. Okay? And so therefore, this map, that's the restriction map, from the equivariant cohomology of M to the equivariant cohomology of NF, the tubular neighborhood, is an isomorphism. Okay? Because of these two zeros. Now, the equivariant cohomology of NF is the cohomology of the homotopy quotient of NF. And I want to say that this is isomorphic to the cohomology of the homotopy quotient of F. That's what I would like to say. Yeah, so if I could say that, then I would have proven the theorem, right? Yeah, so why is this true? NF is an equivariant tubular neighborhood of F.
So F is the deformation tract.
Yeah, so you see, that's right, because a tubular neighborhood is a vector bundle. So NF, since NF is an equivariant tubular neighborhood of F, okay, NF over F, there's a map from NF to F such that it's a G equivariant vector bundle. So, yeah. So here you have F, and then there's a structure of a vector bundle. Okay. It's a G equivariant vector bundle. And so hence, when you take the homotopy quotient, what you get is a vector bundle. You have a vector bundle in which FG maps in by the inclusion as the zero section. So if you have a vector bundle over a space, that space always maps in as a zero section. And you see, there's a deformation retraction of the vector bundle to the zero section, right? Along each fiber. Because each fiber is a vector space, you can retract it to the origin. So, for any vector bundle, there is a deformation retraction for any vector bundle, say E to M, there's a deformation retraction from E to the zero section. Okay? So that means the cohomology of the total space NFG is the same as the cohomology of the zero section. Okay. Yeah. And therefore you have this isomorphism. Okay? And so that gives you the Borel localization theorem. Just a minute. I forgot to put the U here, right? You have to localize first before you get all those zeros. So and so what we have shown is that there's this isomorphism, and so when you put a U there, it's still isomorphic. So therefore, we have an isomorphism from M to NF in equivariant cohomology, which is localized, and this is isomorphic to the equivariant cohomology of the fixed point set F. Okay, so that's the proof of Borel localization. Now let's look at the example of the circle action on the two-sphere. Pardon? That's right, yeah. We need the equivariant tubular neighborhood theorem.
Yes, but then you only need F to be compact,
Right, yeah.
So is it enough to assume F is compact?
But we know that F is compact because it's a...
Take away the assumption that F is compact, just assume F is compact.
Oh, that's right, yeah. Let me see, so... I think you're right. We don't need M to be compact. Yeah. Yeah, we didn't use the fact that M is compact, other than to say that F is compact. So, yeah. Well, okay, that's a very good remark. So, So Borel localization the Borel localization theorem holds for a non-compact manifold M as long as the fixed point set is compact. Yeah, good. So that makes it a lot more useful. Okay, now let's see. Let's see what it says about equivariant cohomology if we don't localize. Okay. So in general, you always have a restriction map. And the restriction map is induced from the inclusion map I. Okay, so I goes from F into M, and then it gives you this restriction map. So in general, yeah. So the inclusion I from F into M induces the restriction in equivariant cohomology, and well, and the restriction map, that's a linear map of vector spaces, okay? And so there is a kernel If you put the kernel here, this is injective, so yeah, the kernel, yeah, this goes in there as the kernel of this, so it's exact, right? So you always have an exact sequence. Induces the restriction I star that fits into an exact sequence. Okay? So now, how do I put something here so that I have an exact sequence? Co-kernel. Okay, so the co-kernel. See, the co-kernel by definition is this space over the image of I star. Okay. So if you put the co-kernel here, then this map will be surjective, and then the kernel of this map will be the image of I star. So it will be exact here. Yeah. Yeah, so this is in general how you make just any map, how you fit any map into an exact sequence. You put the kernel on one side and the co-kernel on the other side. Okay? Now, what does Borel localization tell you about the kernel? Yeah, the Borel localization says that if you localize, okay, when you localize, it's still exact. So if you localize, Borel localization says you have an isomorphism here. And so that means the localized kernel has to be 0, and the localized co-kernel has to be 0. And that says that the kernel is U-torsion, and the co-kernel is U-torsion. So yeah, you have this exact sequence, and then we can localize. Okay? And when you localize, it's still exact. And since this is an isomorphism, so this will be 0 and this will be 0. Okay? Now, suppose you happen to know that the equivariant cohomology of M is finitely generated and it's free over the polynomial ring R of U. So that's the example that we usually have, right? We calculate the equivariant cohomology using spectral sequence, and we find that it's a number of copies of the polynomial ring. It's finitely many copies, finitely generated. So if you know that this is a finitely generated free R of U module, what can you conclude? Well, okay, let's just write down some of the conclusions that we can draw from the Borel localization theorem. So suppose S1 acts on a manifold M with compact fixed point set F. Then okay, then we can conclude, first of all, that the kernel and the co-kernel are U-torsion. The kernel of I star and the co-kernel are U-torsion. And then if in addition HS1M is a finitely generated R of U module, then okay. Now, what do you know about this ring? This is a polynomial ring, R of U. R of U. What's so special about R of U? Yeah, it's a PID. It's a principal ideal domain, right? And so this is a finitely generated module over a PID. Now, if you have a finitely generated module over a PID, what can you say about And in addition, it's a free finitely generated module over a PID. What can you say about a submodule?
So it's also free and finitely generated.
Yeah. Yeah, if you have a finitely generated module over a PID and it's free, then any submodule is free. Okay? But the kernel is U-torsion. So it is torsion. Now, how can it be free and torsion at the same time?
But it's straight zero.
Yeah, it has to be zero. Okay. So that means equivariant cohomology injects into the equivariant cohomology of the fixed point set. Okay? If you know that it is free and finitely generated. And that is in fact the case that we have when S1 acts on S2. Okay? So, so the proof of 2 is that R of U is a PID and a submodule of a free a submodule of a free module over a PID is free. Yeah. But by 1, kernel of I star is torsion. If it's torsion and free, then it has to be 0. So kernel of I star is 0. Okay? Okay, so I think now we can look at this example again of S1 acting on S2 and try to determine its ring structure.
Excuse me, but does that have anything to do with the finite generation?
A submodule of a free module. What does the theorem in algebra say? I seem to remember that it just says the submodule of a free module over a PID is free, right? So you don't really need the fact that it's finitely generated. But a submodule in general, a submodule of a finitely generated module need not be finitely generated. But if it's over a PID, then I think it is true. So yeah. Have to check your algebra textbook. Dummit and Foot. What is the book that you use in algebra? Huh? Yeah, the book that I use is Dummit and Foot, and I think it's in it. Yeah. So yeah, but it's a good question. Yeah, do I really need finitely generated here?
Torsion-free in this case. It's obvious that a module or torsion-free module is torsion-free. Here you are only using torsion-free.
Mm-hmm.
So, and just by definition, if you have a submodule of a torsion-free module, then all four is torsion-free.
Mm-hmm. Oh, so you're saying that I actually don't need the fact that it's a PID.
You don't need PID, you don't finite generate.
Oh, okay. Let me see. So, I see. So you are saying that maybe I can replace 2 by, if in addition, the equivariant cohomology is torsion-free, then the kernel of I star is 0. Right? Yeah, I think you're right. And that's good because then if you have two variables, when you have two variables, then it's not a PID anymore, right? You have two variables. Yeah. That's right, because if you have two variables, U and V, then the ideal generated by U and V is not a PID. That's right. So yeah, it's good. Yeah, it's good not to use the. It's not to use the fact that it's a PID. Yeah. Yeah. So this is a better statement. Now. So let me. Why don't I then just kind of erase all this? Okay. Yeah, that's good. Yeah, let's erase all this. Right. Let's replace it by this statement. Okay? And then it's, then it would be easier to generalize to higher dimensions. Yeah. Okay, so it looks like I don't really have time to do the example today. So we'll do the example next time, okay, on Monday. That is the goal that I've set myself since the very beginning, to determine the ring structure of equivariant cohomology, in a non-trivial example. And if you see how it's done, then you can do it in other examples. Yeah. So basically, the spectral sequence doesn't give you the ring structure. And so you need something else, like the Borel localization theorem, in order to get the ring structure of equivariant cohomology. And in the final problem set, I think I basically ask you to do 3 examples of the ring structure in equivariant cohomology. All right, so we'll continue next week. Yeah.